Myself, Dr. M. Mariappan, Department of Chemistry, SRMI University, Kattangaluttur. This lecture is about the polymers. Before we go into the polymer topics, I'd like to give an outline about the various types of bonding. So there are four types of bonding: covalent bonding, ionic bonding, polar bonding, and van der Waals bonding. A covalent bond exists in hydrocarbons as well as in diamond, and ionic bond exists in sodium chloride. Polar bonds that we can see in water, alcohols, and van der Waals force of attractions generally exist when any, like lizards, when it climbs on the wall. So there are some polymers that are present in biology, so DNA, deoxyribonucleic acids, and RNA, ribonucleic acids, and starch, sugar, proteins, and many more. And natural rubber is nothing but it is polyisoprene, so that we get from the rubber tree. And also another natural polymer is cotton. Cotton is the most common organic material on earth. It is also a primary constituent of wood and paper. Natural polymers, it's a polymer that results from only raw materials that are found in nature. Some of these natural polymers include DNA, RNA, cotton, wool, wood, and some introductions about the polymer. Polymers are very large molecules made when hundreds of monomers join together to form long chains. Okay, so now before we go into the polymers, we should understand what are monomers. Monomers are a single unit. Actually, it's a Greek word. Mono means a single, mer means a unit. When single units are joining together, it ends up with polymers. So polymers means poly means many. Poly means many. Mer means units. So there is a chemical reactions between or among monomers. Suppose if you take 1,000 units of monomers and you add some catalyst, you add some solvent, heat the this all reactants, we end up with the polymers. In general, for addition polymers, we use peroxide as a catalyst. Just now I explained about it. Polymers are nothing but there is a combination of many single units. So it's a Greek word. Polymer is used as a synonym for plastics. One example is polythene. Polythene is a polymer. You can see here. Polythene is a polymer. So here is given here. It is CH2, CH2, N times. It's supposed to be N because we take N number of monomers. What is monomer here? Ethylene. There's one double bond. It's missing here. There's a double bond. Okay, it's supposed to be a double bond. So ethylene to polyethylene. It's supposed to be N at the left side. So right side also supposed to be N. These are some examples for the monomers at the left side. That is ethylene. Okay, and hexamethylene diamine and glycerol. Ethylene where we have a double bond, and hexamethylene diamine where we have two amine groups. Glycerol where we have three OH groups. In polymer, we used to call the functionality. Functionality is nothing but the number of reactive sites. You can see here functionality. Functionality is nothing but number of reactive sites. Number of reactive sites. For ethylene, we have a double bond. So whenever you see a double bond, so then you can say that the functionality of that monomer is 2. Do bonding sites, because the double bond can produce us 2 electrons on dissociation. One will move here, one will move here. We get the 2 free radicals at 2 carbons. That's why we call this as a 2 functionality. In this monomer, there are 2 amine groups, amine 1 and amine 2. Okay, so the functionality is supposed to be 2. Functionality can also be a functional group, can also be a double bonds or triple bonds. The next example, there you can see here, there are 3 OH groups. 3 OH groups. So the functionality of this monomer is 3. The next definition is the degree of polymerization. Degree of polymerization is nothing but the number of repeating units in a polymer chain. Okay, what do you mean number of repeating units? You can see that in the earlier slide. Here, that N is nothing but the degree of polymerization. Okay, suppose just to try to count the at molecular weight of the ethylene, there are 2 carbons and 4 hydrogen. So how we write that molecular formula? 2 carbons and 4 hydrogen, isn't it? So for 1 carbon, the atomic weight is 12. So 2 carbon means 24 plus 4, 28. So the ethylene molecular weight is how much? It's 28. Okay. Suppose if I take 1000 units of this monomer, here what is monomer? Ethylene. How many units? 1000 units or 1000 equivalent, you can say. So 1000 units of this monomer, you get the polymer, and its molecular weight supposed to be what? So here CH2 is here, N is here, so there won't be any loss in molecular weight. I will explain later why there is no loss in the molecular weight. So the molecular weight of the polymer is supposed to be 1000 into 28. So it is 28,000. That is the molecular weight of the polymer. This is the way we find the degree of polymerization. It's very easy. What is the degree of polymerization? The number of repeating units. That definition, this point is important. Number of repeating units. Okay. In other words, molecular weight of the polymer by molecular weight of the more repeating units. In our case, suppose I said 28,000. 28,000 is the, I read here, is equal to, what is the molecular weight of the polymer? 28,000. I put here. What is the molecular weight of the monomer? That is 28. If you divide these two, you end up with 1000. 1000 is the N value. What is the N value? Degree of polymerization. We call this as dP. It's very simple to find. Next, homopolymer. Homo means this is a single monomer. Okay. So the homopolymers are synthesized from a single type of monomer. It can be of ethylene or single type of monomer. This is very important. So I just now I said about it, ethylene to polyethylene. Ethylene is the single monomer. We get polyethylene. Okay, this polymer is called as homopolymer. Homopolymers are consist of chains with identical bonding linkage to each monomer unit. That's what I just now explained about it. So are identical monomers. You can also say that it is otherwise called as identical. So it's a single unit or a same monomer. Okay. So next one is copolymer. Co means more than one. So that means two or more than two different monomers. This point is very important. When they react, we get the polymer that is called as copolymers. So this process is called as copolymerization. And types of copolymers: statistical copolymer, alternating copolymer, block copolymer, graph copolymers. Classification of polymers. In general, there are many types of classifications. The main classification is that we can classify the polymers based on the origin of source, based on the structure, based on the molecular forces, based on the mode of polymerization reactions. Okay, in this there are the four categories. In the first category of origin of source, we have natural polymers, we have semi-synthetic polymers, we have synthetic polymers. Second category, based on structure, we have three types: linear polymers, branched polymers, and cross-linked polymers. Based on the molecular force, we have elastomers, fibers, thermoplastics, thermosetting plastics. Based on the mode of polymerization, we have two types: addition polymers and condensation polymers. Now I will outline about each category. Natural polymers, just now we have explained about it. We discussed about it. Natural polymers are the polymers occurring in nature, like cotton, DNA, RNA, wool, carbohydrates, starch. These things are coming under natural polymers. Semi-synthetic polymer means these polymers can be prepared synthetically in the lab. Here, if suppose some limitations are there in the natural polymers, we treat that polymer with the chemicals or chemical reagents or additives. We improve those properties. So the base is natural polymer. Okay, to the natural polymer we are adding the like additives. So those materials called as semi-synthetic polymers. And the last one is synthetic polymers. These polymers synthesized in the laboratory. The best example is polyethylene. Okay, PVC, polystyrene. There are so many polymers are there. Teflon, etc. These are all synthetically prepared polymers from the laboratory. Okay. Based on the structures, we have three types: linear, branched, and cross-linked. Okay. So linear polymer means it's a straight chain. A polythene is coming under the linear polymer. Just imagine these are all carbons. Carbons is polythene. So branched polymer means you have a linear polymer where you have the branches. That means some groups are attached as a branch. Maybe here, here, here. Okay. If you put Cl as branch, we call it as a polyvinyl chloride. If you put OH, we call this as a polyvinyl alcohol. Instead of Cl, we put OH, we call this as a polyvinyl alcohol. Instead of OH or Cl, if you put methyl group, that's called as polypropene. Okay, this is polypropene, polyvinyl alcohol. This is PVC. Instead of this chlorine OH methyl, if you put phenyl group, so that polymer is called as polystyrene. What is the name? Polystyrene. Okay, so next category is based on the molecular force. Based on the molecular force, there are four categories: elastomers, fibers, thermoplastics, and thermosetting plastics. Elastomers means the plastics or polymers that has the elastic properties. You take a rubber band, try to give a stress at both ends, just try to stretch it. So the length of the rubber band is increasing. Once you leave the stress, it will regain its original shape. So those materials are called as elastomers. That should have the elastic properties. Fibers, jute uh, is the best example for fibrous material. Thermoplastics and thermosetting plastics. Thermoplastics, the best example is polythene, PVC, polystyrene, Teflon. These materials are coming under the category of thermoplastics. Whereas thermosetting plastics, bakelite, urea formaldehyde, and melamine formaldehyde, these things. We will discuss this a little later. Another important question generally will be asked in the exams: differentiate thermoplastics and thermosetting plastics. Based on the mode of polymerizations, there are two categories. One is addition polymers, other one is condensation polymers. So addition polymers means mainly the double bonded monomers. Double bonded monomers will undergo the addition polymers formation, whereas the functional group monomers will undergo the condensation polymerization. Another category, polymers also can be classified as natural synthetic. Just now I have given some examples. Fibrous, plastics, rubbers are coming under the synthetic. Whereas in natural category, we have the functional and structural types. The functional, we have DNA, RNA, global proteins. And the structural types, we have the fibers, cellulose, silk, wood, and gels, rubber, agar, gelatin. So the based on the origin of the source, polymers, just now we discussed about it, natural polymers and synthetic polymers. Natural polymers occurring in nature, okay, cotton, silk, wool, natural rubber. These are all examples for natural polymers. Synthetic polymers, where we synthesize these materials in the laboratory, chemical laboratory. The best examples are polythene, nylon, terylene, and many more, and polystyrene, Teflon, etc. Semi-synthetic polymers we discussed. I have given outline just now. So semi-synthetic means to the natural polymer add some additives to improve its properties. So rayon, and generally people will add some additives to increase the softness, to give coloring in image, and any weakness in the natural polymer can be improved by adding the additives. That we call it as a semi-synthetic polymers. Based on the structure, linear polymers, the best example is a polythene given here. It's the main chain, main backbone. Branched polymers where you see a substitutions as a branch. You can see here branches. Okay. The best examples are PVC, polyvinyl alcohol, polystyrene, etc. Cross-linked polymers are a very hard and stiff materials. Its tensile strength will be very high. Mainly, you can see here there is a cross link between the two different linear chain. That is the point. Okay, network polymers are a 3D network polymers. Bakelite is the best example for this. Bakelite, urea formaldehyde, all the things. It is a completely 3D network polymers. The best examples are bakelite. bakelite, urea formaldehyde, etc. Based on the mode of polymerizations, that means how we prepare the polymers. There are two methods, two classifications. One is addition polymers, other one is condensation polymers. Addition polymers, we add the monomers. Monomers should have a double bond. That's very, very important. Monomers must have a double bond. And you need to have a catalyst, that is a peroxide catalyst. What is peroxide catalyst? That should have OO linkage. You put one carbonyl here and one methyl group, and similarly here you put one carbonyl here, one methyl group. So this group is called as peroxy group. So what happens? Here there is a cleavage, and then what we get? There is a cleavage. It's called as homolytic cleavage. Then two types of this group will be there. This group will be there because both are identical, isn't it? So two times what we get? CH3 COO radical species, isn't it? And then further dissociation with the elimination of carbon dioxide, we end up with two times methyl radical. This methyl radical we can call it as a initiator, so I radical. Okay, this I radical only will go and attack the monomer. So there are three steps in this reaction: initiation and propagation and termination. Initiations where the initiator will go and attack the monomer. Initiators will go and attack the monomer. That is I radical. Okay, that's methyl radical will go and let us start with ethylene. Okay, ethylene, what happened? This double bond will be replaced with a radical species here. Radical species here. Double bond after it is dissociated, and this I radical and methylene radical will combine. It makes a bond, covalent bond. Okay, so we should write like this: I covalent bond CH2 CH2 radical species. Understand? So this will undergo the propagation. That means this will react with another monomer, and then again another monomer, another monomer. The chain length will be improved. It will be increased. That is called as propagation. And termination is nothing but somehow we have to stop the reactions because it's a radical species. It's a polymer reaction, it's highly reactive. At one stage after we get the satisfied material, we have to stop the reaction. That we call it as a termination. In some cases, we add some reagents for terminations. In some cases, the intermediate itself will undergo the no, we will release the hydrogen that will quench the radical species, and we get unsaturated polymer. Next one is condensation polymerization. Condensation polymerization is nothing but there is a condensation reaction. What do you mean by condensation? More than one monomer. See here, two different monomers are reacting together, we get a polymer. Plus assembles byproduct. Here byproduct means there may be a chance of water or methanol or methyl chloride, hydrochloric acid, etc. Okay. The best example is nylon 6,6. I discuss the reactions a little later. Nylon 6,6, what we do? We take adipic acid, that is a monomer 1, and hexamethylene diamine, that is monomer 2. They both will react to get the polymer. This is M1, monomer 1. Okay. This is M1, M2. M1 means monomer type 1. M2 means monomer type 2. Okay. So there's nothing but individual chemical reaction with elimination of water molecule. The byproduct is formed and condensed out. It creates water. This reaction is slower than addition polymers. because addition polymers are radical mechanisms. Here it is a condensation, so chemical reactions. Next point is functional group is must. Okay, so the functional group is must for this reactions. What are the functional groups? Functional groups can be of OH, it can be of NH2, can be of carboxylic acid. Understand? This image which supports the linear branched and cross-linked, cross-linked and crossed and network polymers we discussed just now. And next topic is tacticity. Tacticity is nothing but the orientation of the monomeric units or functional groups in the polymer. Okay, or functional groups in the polymer. So ducticity do affect the physical properties of the polymer because of the orientation. There are three types of ducticity. The first type is isotactic. Iso means same. The reactions you can see here, we have a polymer that is polystyrene. We start with styrene. Here there is a phenyl group. Okay. So what happens after the polymer reactions? You see that all the phenyl groups are in the are substituted as a branch at the bottom side. So that's why we call it as a isotactic. Iso means same side. Next one is syndiotactic. Syndio means it's a Greek word, alternative. Okay, alternative. That's very important. So the same styrene, a number of styrene units, you do the reactions. After the reactions, we get the polymer in which, see here, the phenyl group here it's at the bottom, here it's at the top. Here is at the bottom, here is at the top. So this is what we call it as a alternative position in the polymer back chain. Okay, that is called as syndiotactic. Syndio means what? Alternative fashion. Next one is adactic. Adactic means irregular. Adactic means what? Or random arrangements. There won't be any order of arrangements. Same styrene, when you do the reactions, see there is a polymer formation, polystyrene, where two phenyl groups are at the bottom and two phenyl groups are at the top. Maybe in the next category, one may be at the top, three may be at the bottom, or one may be at the bottom, three may be at the top, like that. There aren't any order arrangements of these phenyl groups. That is called as atactic. Atactic is irregular or randomly. Okay.